Okay, welcome to the sixth and final section of Chapter 4. We're going to talk now about these things called inverse matrices, and we're going to look at how we can use them to solve 2x2 systems of equations. Yes, believe it or not, there is still yet another way to solve systems of equations using matrices. But first, let's just talk a little bit about what inverse matrices are. So, before we can talk about inverse matrices, there is one other definition I have to explain to you, and it's this thing called an identity matrix, and we use the letter capital I to abbreviate it. An identity matrix is a square matrix that when you multiply that matrix by another matrix, you keep the identity of the matrix. So it's sort of like, the identity of multiplication of numbers. 8 times 1 is 8, and we call 1 the identity element for the same reason. These two matrices that I'm pointing out here, these are the 2x2 identity matrix and 3x3 identity matrix. Quite simply, it's just 1s down the main diagonal and 0s everywhere else. If we wanted to come up with a 4x4 identity matrix, we'd do the same thing. We'd have a diagonal of 1s and then 0s everywhere else. Okay? Why this is important is because it kind of leads into this more important matrix that we're going to look at in this section, inverse matrices. Okay? A to the negative first power, we don't say it that way, we call it A inverse, but that's what it looks like. That's the symbol for an inverse. So we say A inverse is the inverse of matrix A if when you multiply A inverse times A or A times A inverse, you get this identity matrix back. Basically, they undo each other with multiplication, kind of like how any number and its reciprocal are multiplicative inverses with the real numbers. Same kind of idea here, except we're talking about matrices. Okay? So first thing I want to do is I want to verify whether or not a pair of matrices are inverses. So the way we do that is we multiply them together and we see if we get the identity. So for the first example here, if we do x times y, we get, so we'll set it up. There's matrix x times matrix y. So we go, remember, across the first matrix, down the second matrix, or the column of the second. So we've got 3 times 1 is 3. Negative 2 times 1 is negative 2. That's 1. Negative 1 times 1 is negative 1. Positive 1 times 1 is positive 1. That adds to 0. So far, so good. 3 times 2 is 6. Negative 2 times 3 is negative 6. That also adds to 0. Negative 1 times 2 is negative 2. 1 times 3 is 1. This does check out. These are inverses of each other because, indeed, we get the identity. Let's try PQ. So we'll set up P first. So we'll go across and then down. So 3 times 1 is 3. Negative 1 times 2 is negative 2, so that adds to 1. We're looking good so far. 4 times 1 is 4. Negative 2 times 2 is negative 4. That adds to 0. 3 times negative 3 is negative 9. Negative 1 times 4 is negative 4. That adds to negative 13. We needed that to be 0. These are not inverses. Sad day. Okay, because they do not multiply. PQ does not equal the identity, so they can't be inverses. All right, so now that we can see how a pair of matrices that are inverses interact, let's talk about how we can figure out what an inverse would look like if we're given a matrix. So here's the rule for that. All right, it's right here. You might want to pause the video and make sure you have this written down in your notes. The inverse of A, and if these are the 4 elements, A, B, C, D, the way we get A inverse is first, we rearrange some of the elements. Notice the change. The left diagonal gets flip-flopped. The A moves down, the D comes up. The right diagonal, the placement stays the same, but the elements, you take the opposite sign of them, negative B and negative C. All right, so after you rearrange all that, the next thing you do is you multiply all these elements by 1 over the determinant of the original matrix A. Okay? The most important thing in this definition is this idea here that the determinant of A, cannot equal 0. Because if it does, you have no inverse. So that's a surefire way to see whether or not a matrix has an inverse, is if its determinant is 0. Okay? So here's the first one. First thing we'll do is we'll get the determinant of A. And remember, that's going to be, we'll do -1 times -2 is positive 2. 8 times 0 is 0. So the determinant of A is 2. So that means A inverse is going to equal 1 over 2 times a little bit of a rearrangement of these elements. So the -1 and the -2 flip-flop. And then the 0 and the 8 change signs. Now, we don't change the sign of 0 because 0 doesn't have a sign. Okay, to finish, we're just going to multiply all these numbers by 1/2. So I see -1. Half of 0 is still 0. Half of -8 is -4. And then half of -1 is -1/2. So this matrix here is the inverse of A. And if you wanted to check it, you could multiply these two together and you would get the identity. All right, let's look at the next example. So we'll do the determinant of U, and our matrix U is -4, 6, -2, 3. So we'll do our cross products. -4 times 3 is -12. 6 times 2 is also -12. Uh-oh. The determinant of this matrix is 0. We said the determinant can't be 0. So what this means is U inverse does not exist. This matrix does not have an inverse. There is no 2 by 2 matrix that when multiplied by this one will get us the identity. Okay? How about you try some examples? There's some on the note sheet. Go back and watch this if need be. When you're ready to pick up where we left off, you can restart the video. Alright, so now that we've figured out how to come up with inverses, the next step is to be able to apply these in order to solve systems of equations. The good news is, unlike Cramer's rule in the last section, we're not even going to deal with the 3 by 3s. We're only going to stick with 2 by 2 systems and 2 by 2 matrices. To understand the way we do this, this is the part that gets a little technical. We're going to convert the system into a matrix equation, and the form of the equation looks like this: AX equals B. And all of these are matrices. That's why I'm using capital letters. The A is the coefficient matrix, like I have down here, and B is a column matrix using the numbers on the right-hand side. So that means, in my example, the system x plus 2y equals 9 and 3x minus 6y equals 3 becomes the 2 by 2 matrix of the coefficients, 1, 2, 3, -6, times this variable matrix we call it. It's just a column matrix of x and y, equals the column matrix 9, 3. And if you notice, if you actually multiply this left-hand side, you do get the system again, because you get 1 times x plus 2 times y. Oh, that's that. 3 times x plus -6 times y. That's that, equals 9 and 3. So it sort of makes sense. Okay? Now, once you get it in this form, the way we solve for the x and the y right here is we use this little rule. Now, in class, I'm going to algebraically show you this and prove to you why this works. But for right now, through the video, just trust me that this is how it's going to work. xy, this matrix big X that I defined here, the variable matrix, equals A inverse times B. Now remember, order matters. You got to put A inverse first on the left. Otherwise, we may not be able to answer the question correctly. Actually, if you do A inverse on the right, it's not defined anymore because of the dimensions we talked about before. So that's what we have to do. We have to basically turn the system into this equation, take A inverse and multiply it by B, and then we're done. All right, so let's do some examples of that. Okay, so we have a system, -x plus y equals 3, -2x plus y equals 6. So if we convert this into a matrix equation, I'm going to put in kind of the blank matrices to give you an idea of what we're doing here. AX equals B. So our matrix A contains -1, positive 1, -2, positive 1. Our X matrix has our letters, And then our B matrix has what's on the right-hand side. So according to the last slide, we said that X equals A inverse times B. So we've got to get A inverse first. So we've got to find A inverse. So let's do that now. So we got to get the determinant of A before we do anything. So we will cross multiply. We get -1 minus -2. The determinant is 1. So A inverse will equal 1 over 1. And then we've got to rearrange our entries. So again, to find the inverse, we flip-flop the left diagonal. So the 1 moves up top, the -1 moves down. And then the other two entries, we take opposite signs. So the 1 becomes a -1, and the -2 down at the bottom left becomes +2. We multiply all that by 1, which is kind of trivial because it just keeps all of its values. So this right here is A inverse. So the next step we've got to do is we've got to actually figure out what A is going to be. Or excuse me, what X is going to be. And we do that by taking this A inverse and multiplying it by B. So we get 1, 2, -1, -1 times B, which is 3, 6. We're going to get another column matrix, because remember, we have a 2 by 2 times a 2 by 1, so we're going to get another 2 by 1. 1 times 3 is 3. -1 times 6 is -6. 3 plus -6 is -3. Now we'll do the bottom row times the column. 2 times 3 is 6. -1 times 6 is -6. That adds to 0. So that means the solution to this system has got to be -3, 0. Not bad, I hope. We'll do a couple more. All right, so here's a second example. So we have 3x plus y equals 3, 5x plus 3y equals 6. Okay, so let's start with our coefficient matrix. It's going to be 3, 5, 1, 3. Okay, first step we've got to do is we've got to find A inverse. So let's take the determinant. 3 times 3 is 9. 5 times 1 is 5. 9 minus 5 is 4. So this means A inverse is going to equal 1 over 4, because it's 1 over the determinant, times a shift of these elements. Well, there's 3's on both entries in the left diagonal, so we are technically changing their position, but it's the same number, so it doesn't really look like we did anything. The only thing we have to do here is make the 1 a -1 and the 5 a -5, and then we just have to multiply everything by 1/4. So we have 3/4 and -5/4 in column 1, and then -1/4 and +3/4 in column 2. So this is A inverse. The last thing we have to do now is we have to come up with what X is, and we said X is A inverse times B. So A inverse is 3/4, -5/4, -1/4, 3/4. We're going to multiply that by 3, 6. All right. Hope we don't mind fractions here, ladies. Let's handle it. 3/4 times 3 is 9/4. -1/4 times 6 is -6/4. That adds to 3/4. -5/4 times 3 is -15 over 4. 3/4 times 6 is 18 over 4. I believe that also adds to 3/4. So it looks like X is 3/4 and Y is 3/4 is going to be the solution to this system. All right, let's look at one more. This is an interesting one. -x plus y equals 4. -x plus y equals -4. Okay, you might already see the writing on the wall here because we spent a lot of time talking about systems. The left-hand sides of both of these equations are exactly the same, but the right-hand sides are not. So you can already probably tell me this is going to be no solution. But let me show you how matrices can prove it. So we get our coefficient matrix of -1, 1, -1, 1. Right? And we try to take its inverse because, as we said, X equals A inverse times B. So to get the inverse, we've got to do 1 over the determinant, and then we've got to flip-flop the left diagonal and then take the opposites of the right diagonal. So I already set up the elements of the inverse. All I got to do is take this determinant from the original A, and multiply 1 over that value times the new matrix. So let's do the determinant of A. Negative 1 times 1 is negative 1. But negative 1 times 1 is also negative 1 for the other diagonal, and when we subtract them, we get 0. And like we said, if the determinant of a matrix is 0, this means A inverse does not exist. And if A inverse does not exist, you can't do that up there to figure out what x. So that means there is no solution to the system. Okay? So it's kind of easy. If you get this matrix A and find out that its determinant is 0, you're done with the problem. There's no solution. Okay? All right, with that, I have some examples of some systems for you to try. If you have any questions, feel free to ask them in class. And with that, I wish you a good